Welcome back to Honors Calculus. In this video, we're going to be starting into the idea of Riemann sums, which is a very technical part of calculus, but based on a very simple idea. That idea is, how do you calculate the area of an arbitrary curve? So let me get my head out of the way and show you exactly what I mean here. Completely getting away from the idea of functions, graphs, or anything like that, I want you to imagine looking at a map. And looking at a map, you see a lake which has a shape something like this. And we want to calculate the area of this shape. Our map very conveniently has a key, perhaps that distance on the map is 1 mile. There are a couple of different ways that you can approach calculating the area of this shape. The one that I want to use here is an idea called the trapezoid rule. And the idea is essentially that I'm going to draw a bunch of, and I'm going to choose vertical lines, although you can do this in a couple of different ways. I'm going to choose a bunch of vertical lines, equally spaced and parallel. Right. So the idea that the lines that I'm drawing are parallel and they're equally spaced, right? Each neighboring pair of lines is exactly 1/3 of a mile apart. And I could extend these lines out, but the only part of the line that really matters is the part that falls inside of our arbitrary curve. So that's the part that I'm trying to stress here. And what we want to do is connect the dots. All right. On the edges, I can, I guess, continue on something like that if I want to, although I'll probably just leave those off and say that's close enough. So what I want to do next is simply draw some more straight lines, and I know these are going to be a lot less straight than the ones I had before, but I want to draw some straight lines connecting each neighboring pair of lines at the top and at the bottom. Essentially, I am taking the nice smooth curve that is the shore of this lake, and I'm replacing it with a whole bunch of straight lines. I happen to have chosen a shape that was fairly smooth, so that for the most part, I ended up following along with the curve, although I could be off by a little bit. So the next thing that I want to do is measure the length of each of these lines. I'm going to call the one at the left L0, and then I have L1, L2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. We do always start at 0 because it gives us the very convenience of that region is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We've divided the lake into 13 regions, and the last number that we count to is number 13. We could also do this from 1 to 14, but the numbering would be a little bit weird in that regard. So the area of a trapezoid is 1/2 times the sum of the two parallel bases that make up the trapezoid times the height, the distance between them, which in this case is a width. We'll call that h. So A2 is 1/2 L1 plus L2 times h. A3 is 1/2 times L2 plus L3 times h, and so on down the list. In order to calculate the total area of the lake, I simply want to add all of these things together. The total area of the lake is the area of the first trapezoid plus the area of the second trapezoid. And we had 13 total trapezoids, so this will go all the way to a 13. And then just substituting in that formula of a trapezoid for each one of those. In this formula, I want to point out that every term has a factor of 1/2, and every term has a factor of h. So I can factor those out. And I'll write h over 2 in front here. And then I have L0 plus L1. And I have L1 plus L2. And it keeps going until I get to the end and I have L12 plus L13. And what I want you to notice here is that most of the lengths show up twice. L1 shows up in the first trapezoid and again in the second trapezoid. L2 will show up in the second and then again in the third. The two lengths that don't show up twice are L0, which is on the far left side, and L13, which is on the far right side. So we have to be a little bit careful about those. Other than that, we've got L0 plus 2L1 plus 2L2, 2L3, and it keeps going until we get to 2 times L12, and then just 1 of L13 at the end. So this is the trapezoid formula for our particular use case where we were able to divide the lake using 13 well, 14 vertical lines, dividing it into 13 regions. In general, we are looking at dividing our figure into some unknown n regions. Which means that instead of going from 0 to 13, we're going to go from 0 to n. The area here is h over 2 times L0 plus 2 times L1 plus 2 times L2 plus dot 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 plus 2 times Ln minus 1, and then plus a single Ln. When it comes to generalizing this formula, I really don't like the fact that we have to keep in mind the first and last have a 1 and everything else has a 2. So the next thing I want to do is kind of play around a little bit with the formulation here. And I'm going to leave L0 off for just a moment. And I'm also going to play a cute trick here. And the fact that Ln didn't have a 2 in front bothered me as well. I'm just going to introduce that 2 in front. And it's only here at the end I'm going to put back my L0. And because I put that 2 on Ln, I have to fix that somehow. I do that by subtracting an Ln right back off. All right, that's a little bit goofy. I took something that was fairly straightforward and I made it a lot more complicated. And the reason I made it a lot more complicated is I can now distribute h over 2 a lot nicer because the first n terms have a 2 that will cancel out the 2. So I've got L1h plus L2h plus dot 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 plus Ln h for those first n terms. And then the last part, I'll just leave written a little bit like that, which is kind of goofy, but it's okay. Because for the first n terms, we have a really convenient formula of just adding a bunch of stuff together. And adding a bunch of stuff together is exactly what summation notation was invented for. K goes from 1 to n of Lk times h, plus that stuff that didn't quite fit the mold, h over 2, L0 minus Ln. All right, so we've taken this idea of a trapezoid formula for calculating the area of an arbitrary shape. We took a formula that was pretty easy to remember and we turned it into something that kind of looks like a nightmare. Doesn't exactly feel like the right thing to do. So let's get back to it and try to justify why we did such a strange thing. I want to take a look now that we've established this idea of the trapezoid rule, used processes from geometry to get some understanding of where it's coming from. Let's look at a figure that we can actually work with. The problem with arbitrary curves is that in order to measure them, you have to get a ruler and actually draw the parallel lines and measure their lengths, which is perfectly fine in a geometry class, but not so much in a calculus class. So our goal here now is to find a shape where we can actually work with it. So consider here the curve y equals 4 minus x squared. And I want to calculate the area of this bounded region. So we're going to take the upper part of the curve, being the graph y equals 4 minus x squared, and the lower part of the curve being the x-axis. And my goal is to calculate the area between these two shapes, or to calculate the area between a curve and the x-axis in general. Right? Our goal is to, again, divide into n regions, only this time, instead of just talking about something in arbitrary sense, we're talking about a specific part of the x-axis. So we want to divide the interval from a to b into n regions. And if we divide the interval from a to b into n regions, then the width of the interval, which we're going to represent this time using delta x instead of h, is going to be the total length of the interval, which will be b minus a, divided by the number of pieces. B minus a over n gives us the length of each piece when we chop this interval into n pieces. And then our argument for the height. If we pick a particular point, well, we have to figure out how to get to that point. If we start at A and we go over k places, then we're looking at x equals A plus k times delta h. And to find the height at that particular x value, we simply evaluate our function f at a plus k delta x. So L0, the height at the left endpoint, would be f of a, and Ln, the height of the right endpoint would be f of a plus n delta x. Now our right endpoint we said was going to be b. So this should be f of b, and it turns out it is. If we substitute in the definition of delta x, we're looking at f of a plus n times b minus a over n. The n's cancel each other out, so we have f of a plus b minus a, which is just f of b. So this definition, this idea of using the trapezoid rule to analyze our function, is now given a more precise meaning. And the area is still the sum. K goes from 1 to n of LK H plus H over 2 L0 minus Ln. But our LK, as we just said, is f of a plus n, sorry, not n, a plus k times delta x, and our h is delta x. L0 is again f of a, Ln is f of b. This formula is called a Riemann sum, named after a mathematician named Riemann, who really did a lot of work with the analysis here. One of the main springboards that Isaac Newton used in his development of calculus, or Leibniz in his independent development of calculus. Before I show you an example, I do want to mention that there are 4 different formulas that are used to evaluate a Riemann sum. There is no better or worse between the 4 formulas. It's just that there are 4 different ways to draw figures to approximate the area of a arbitrary curve. I'm using the one called the trapezoid method, which is the most accurate, but also the hardest to work with. There is the left side rule, the midpoint rule, and the right side rule, which use rectangles instead of trapezoids, so they're a little bit easier to work with, but they also cause a little bit more of a mess. Regardless, we started an example with a particular function. So we have the formula here for a Riemann sum. We have our function f of x is 4 minus x squared. And we want to calculate the area that is trapped by 4 minus x squared on the interval from -2 to +2. And in order to do this, we are going to need to make a decision. We need to decide how many regions we are going to divide this figure into in order to make our approximation. And we can use literally any number we would like. It all works out about the same. The bigger the number, the more accurate your area will be. But at the same time, the bigger the number, the more annoying the process is going to be. Let's choose a relatively middle ground number and divide this region into 20 pieces. So with that idea, the first thing I'm going to do is calculate the size of delta x. Delta x is b minus a divided by n. B is 2, a is -2, n is 20. So we're looking at 4 over 20 or 1/5. The other piece that we're going to need in this process, well, we're going to need f of a, which in this case is f of -2. Four minus -2 squared is 4 minus 4, which is 0. We're going to need f of +2, which is 4 minus 2 squared, 4 minus 4, which is again 0. And we're going to need a nice expression for f of a plus k delta x. Right? Again, a is -2. K is going to be a parameter that's going to be showing up in our result. And delta x is 1/5. So f of -2 plus k times 1/5 is 4 minus -2 plus k times 1/5 squared. Squaring this, we'll get -2 squared, which is +4. We'll get -2 times 1/5 times 2, which is -4/5 times k. And then we'll get 1/5 squared, which is 1 over 25 times k squared. Distributing that subtraction, 4 minus 4 is 0. And then we have minus minus, which is plus 4/5 k, and then minus 1 over 25 k squared. And with that, we can plug all of this information into the formula for the Riemann sum. A is the sum. K goes from 1 to n, which is 20, of f of a plus k delta x, which in this case is 4/5 k minus 1 over 25 k squared, times delta x, which is 1/5. Then plus delta x, which is 1/5 over 2, times f of a, which is 0, minus f of b, which is also 0. Very conveniently, that last thing just all goes to 0, which makes our lives so much easier. Distributing the 1/5 and kind of playing around with the summation here, we have that a is going to be 4 over 25 times the sum. K goes from 1 to 20 of k, minus 1 over 125 times the sum. K goes from 1 to 20 of k squared. And remembering the rules of summations, the sum on k is n times n plus 1 over 2. And the sum on k squared is n times n plus 1 times 2n plus 1 over 6. We can punch that into a calculator right now, or we can play around a little bit with reducing fractions. So we've got a 4 over 2, which is going to leave me with a 2 in the numerator. We've got 20 over 25, which is going to leave a convenient factor of 4 in the numerator and 5 in the denominator. And on the second one, we've got the common factor of 5 again. So it'll be 4, that'll be 25. 21 is 3 times 7. And 6 is 3 times 2. And hey, this 4 and that 2 will cancel out, leaving me just with another factor of 2. And let's see, 2 times 4 is 8. 8 times 21 is 168. 2 times 7 is 14. 14 times 41 is 574. I guess we can get a common denominator by multiplying 168 over 5, top and bottom, by 5. That'll be 840. Right. Convenient trick of multiplying by 5. It's the same thing as dividing by 2 and then multiplying by 10. So half of 168 is 84, put a 0 at the end, 840. And then 840 minus 574 looks like it's going to be 136. And that's my calculation for the area here. We can divide that out if we want to. That's 5 and 11/25, which is also 5.44 if you want a decimal. And again, if I had a calculator on hand, I probably would have just used it way up here and gotten immediately to 5.44, but I didn't have a calculator on hand, so I had to work things out the long way. So I would like you to take a look at the function f of x equals x minus x squared. First, I would like you to graph y equals f of x. You can either graph it by hand, or you can use Desmos or other computer software to get a graph digitally. I'm not picky about how you go about it. I just want to see the graph. And when you are looking at the graph, you should be able to identify some region where the graph is bounded above by y equals f of x and bounded below by the x-axis. Determine the interval on which that happens. And then using n equals 7, so dividing this up into 7 trapezoids, calculate an approximation for the area of that region. See what you can do with this problem, and I'll see you in the next video.